When the plane vanished without a trace, the world and the aviation industry was stunned. When Malaysia Airlines Flight MH370 lifted off Kuala Lumpur on 8 March 2014, nobody expected a routine short-haul international flight to become the single most baffling disappearance in modern civil aviation. The aircraft, a Boeing 777-200ER, registered 9M-MMRO, was carrying 239 people bound for Beijing. Within hours, the aircraft's ordinary electronic heartbeat went silent. Primary and secondary radar contact ended, ACARS messages stopped, and the aircraft's transponder no longer identified it to civil air traffic systems. What followed was a decade of multinational searching, scattered debris washing up on distant shores, and an investigation that never reached a definitive conclusion. This shocked the aviation industry because in 2014, twin-engine, fly-by-wire airliners like the 777 were assumed to be trackable and forensically resolvable. Yet MH370 exposed a critical blind spot. In some parts of the world, a modern airliner can still slip off the map and stay missing. Today we'll walk the timeline, explain the forensics, examine the technical evidence, and look at what MH370 changed and what remains frighteningly unresolved. At the core of the publicly available data are three interlocking strands: radar ATC records, satellite communications handshakes, and later physical debris recovered on shorelines. Flight MH370 departed Kuala Lumpur at 00042 MYT. Routine radio contact and ACARS updates ceased as the flight crossed the South China Sea. Military primary radar briefly tracked the aircraft as it deviated from its filed route and turned west across the Malay Peninsula. After that, civil radar coverage was lost. Later analysis of satellite metadata, not full voice or data from an Inmarsat ground station, produced a series of time-stamped log-on and handshake exchanges that placed the aircraft somewhere along a set of arcs in the southern Indian Ocean, the most discussed being the so-called 7th arc. Those arcs are probabilities, not precise coordinates. They constrain where the aircraft could have been when the final satellite exchange occurred, but they do not supply an impact point by themselves.
Technical primer. The Boeing 777-200ER is a long-range twin-engine jet with robust systems: ACARS for automated system reporting, a secondary surveillance radar, SSR, transponder that replies to ground SSR interrogations, and SATCOM SDU units that send periodic log-ons or pings to satellites. If either ACARS or the transponder is deliberately turned off, or if electrical power or communication systems are lost, those feeds stop even while an aircraft may continue to fly. That difference, no signal versus no airplane, is central to what investigators can infer and what they cannot. On fuel and performance, the 777-200ER's published fuel capacity and range figures anchor endurance calculations used by analysts to determine how long it could have remained airborne after losing contact. A multinational search effort followed in 2014 to 2017 that became one of the most expensive and technically ambitious in history. Surface searches, aerial patrols, and underwater mapping of large ocean areas were carried out by several nations and agencies. Confirmed debris began washing ashore in 2015 on western Indian Ocean coasts, providing the first physical link to the southern Indian Ocean theory. The official Malaysian safety investigation concluded in 2018 that without the main wreckage and flight recorders, investigators could not determine the definite cause. Those gaps are the reason this mystery remains active more than a decade later. Here's how this works. After the transponder and ACARS ceased, the only continuing machine-level communications detectable to investigators were the Inmarsat satellite log-on sequence, short metadata-style exchanges showing that the aircraft's satellite data unit, SDU, was still responding to the ground network. Inmarsat's team and independent analysts used Doppler and timing analysis of those handshakes to infer a set of arcs, essentially rings at certain distances from the satellite, and a small set of candidate tracks crossing the southern Indian Ocean. That produced the 7th arc hypothesis. The aircraft's last known satellite exchange sat somewhere on that arc, which became the focal line for deep water search planning. It's important to stress, the The satellite data give timing and range constraints and, with Doppler, speed heading hints. They do not provide a final GPS coordinate. The resulting search boxes were therefore probabilistic, not deterministic.
The 777-200ER's fuel capacity and performance charts are central to endurance modeling. Boeing's data for the 777 family places a 777-200/200ER's usable fuel on the order cited in manufacturer planning documents and enables analysts to estimate possible flight durations given standard fuel burn and payload. Using those figures, most technical reconstructions show the aircraft could have remained airborne long enough to reach the southern Indian Ocean arcs if it continued to fly after radar contact, supporting the fuel exhaustion into the ocean scenario. That said, fuel calculations alone cannot distinguish an uncontrolled fuel-starved descent from a controlled ditching or other sequence. They only bound how long flight could continue after loss of communications. Now consider failure modes. Electrical or catastrophic structural failures can extinguish ACARS and transponder data, but massive structural loss at cruise would likely leave other observable signatures or early debris patterns inconsistent with the later confirmed flaperon finds. Conversely, human intervention, deliberate shutdown of communications or routing changes could create the exact telemetry signature observed while leaving the aircraft otherwise flyable for hours. Investigators have explored both instrument failure and deliberate action hypotheses. The evidence available, satellite handshakes and the lack of flight recorders, rules neither completely in nor fully out. That is why the investigation has been careful about conclusions. From mid-2015 onward, pieces of confirmed or strongly suspected MH370 origin began to appear on western Indian Ocean shores, most famously the flaperon found on Reunion Island. Serial number identification and subsequent laboratory work tied at least a handful of items to a Boeing 777, providing the first physical confirmation that debris from MH370 reached the western Indian Ocean. Importantly, CSRAO and ATSB drift modeling used the timing and locations of debris finds to constrain likely origin sectors on the 7th arc. These oceanographic models point towards segments of the southern arc as the most likely impact corridor, but cannot pinpoint an individual impact site because ocean drift is chaotic and sensitive to storms, time and water, and object shape. In short, debris proves an Indian Ocean outcome and helps narrow the search, but by itself, it does not give the final wreckage coordinates.
Searching for wreckage on the deep ocean floor is a different technical problem from aerial search. Modern deep searches use side-scan sonar to map broad swaths and autonomous underwater vehicles, AUVs, to visually inspect anomalies. The 2014 to 2017 searches covered tens of thousands of square kilometers with high-resolution sonar, but did not locate the main wreckage. Private companies later proposed new searches using improved AUVs and refined search boxes informed by improved drift models. The commercial firm Ocean Infinity signed a no-fine, no-fee style contract, offering payment only if the wreckage is located within a designated search area. A high-incentive model that nevertheless faces weather windows, seabed complexity, and operational risk. The reality, mapping and investigating a 15,000-plus kilometer squared deep ocean area is feasible technically, but remains extremely costly and challenging logistically. First, tracking policy. MH370 forced regulators and airlines to rethink global tracking standards. The industry accelerated interest in space-based ADS-B and better global SATCOM-based tracking so that an airliner's position can be known more continuously, even over oceanic sectors beyond radar coverage. That shift is visible in both airline procurement decisions and in regulatory conversation about near real-time reporting and remote tracking standards. The upshot for operators is clearer. Regulators now expect better positional data coverage for oceanic flights, and the industry has invested in satellite tracking solutions to reduce the risk of disappearing aircraft. Second, financial and operational consequences. Malaysia Airlines suffered immediate reputational damage, severe short-term revenue impacts, and large insurer claim settlements. Public trust and route economics shifted. The carrier's recovery involved rebranding and financial measures in the years after 2014. Insurers and reinsurers also learned from the scale and complexity of long-duration search operations and claims, which influence commercial aviation liability and contingency planning. These are quantifiable, industry-level impacts that continue to inform airline risk assessment and crisis preparedness. Third, the search and ocean mapping market. The Ocean Infinity no-fine, no-fee approach, a private sector model with a large contingency payout, reported at around $70 million if the wreckage is found within the contracted area, signals a new equilibrium. High-stakes private searches leveraging advanced robotics may supplement or, in some cases, replace time-limited government efforts. That model has policy implications for how future high-profile searches will be structured and financed.
We should be disciplined. No speculation without basis. With the evidence and technology available today, there are 3 realistic, evidence-based scenarios. Number 1, targeted discovery. Improved AUV coverage, better processing of sonar anomalies, and luck, combined with a focused, weather-permitting search of a high-probability segment of the 7th arc, could reveal the wreckage and flight recorders. Ocean Infinity's recent contract and modern robotics make this technically plausible, though not guaranteed. If found, the industry would gain final crash cause insights and a firm closure for families. Aircraft tracking and safety recommendations would follow accordingly. Number 2, partial closure via debris or new evidence. Intermittent finds of new debris or improved drift modeling convergence could refine search boxes and enable more targeted operations without a full, immediate discovery of the fuselage. This would slowly improve probability estimates and perhaps allow future targeted campaigns to be more efficient. CSIRO's drift work illustrates how incremental advances move the needle, but only so far. Number 3, prolonged uncertainty. The aircraft may remain undiscovered if seabed complexity, remoteness, and funding constraints prevent exhaustive survey. In that case, the aviation industry still benefits. MH370 has already catalyzed stronger tracking standards and improved deep ocean search tools. Those systemic fixes reduce the chance of a repeat, even if this particular mystery remains unsolved. To summarize, we know enough to place MH370's final activity along arcs inferred from satellite handshakes and to say with high confidence that debris found in the western Indian Ocean originated from a Boeing 777. What we do not have is the main wreckage in the flight recorders, the definitive machine evidence that would answer the fundamental question of why. That absence is why, more than a decade later, MH370 continues to matter to airlines, regulators, and families. It exposed a systemic gap in global aircraft tracking and pushed both public sector and private sector actors to accelerate technical and policy fixes. We also need to be clear and responsible. Where physical evidence is lacking, we avoid speculation that outpaces the data. If you found this breakdown useful and want a technical follow-up, a deep dive into Inmarsat Doppler analysis, the CSIRO drift modeling methodology, or the specifics of modern AUV search workflows, tell me in the comments and I'll produce a dedicated technical episode. Remember to subscribe for more aviation content. If you want the visuals for this episode, I can supply callouts for on-screen graphics and timing notes for editors. Thanks for watching.